Hello and welcome to the last three sections of Chapter 5. Today we're going to take a look at multiplying special products of binomials, some power rules, and dividing polynomials. We'll start with the product of sums and differences. So for example, x plus 2 times x minus 2. Here we have two terms added together times those same two terms now subtracted. We'll multiply this out normally. X times x gives me x squared. X times negative 2 minus 2x. Now 2 times x plus 2x, and 2 times negative 2 minus 4. My two middle terms are like terms, so I can combine them. And I'm left with x squared minus 4, since those two middle terms cancel each other out. What we can gather from this is when I have a product of sums and differences, all that will matter are my first term and my last term, since my two middle terms will always cancel each other out. So I just need to multiply my first two terms together and my last two terms together to get my answer. Another example here, we can take x plus y times x minus y, and this gives us x squared minus y squared. And we see here we take that first term times itself and the last term times itself. A more complicated example, let's take 2x minus 3y times 2x plus 3y. Here again, multiplying the first two terms, we get 4x squared, and our last two terms minus 9y squared. Again, always the first two terms together and then the last two terms together. Again, keep in mind this only works when you have a product of sums and differences. Next, we'll take a look at squaring binomials. Say, for example, we have x plus 2 squared. This is the same as x plus 2 times x plus 2. If we multiply this out, we get x squared plus 2x plus 2x plus 4. We add our two middle terms together and we get x squared plus 4x plus 4. What we see here is when we're squaring a binomial, our two middle terms are always exactly the same. So what we can see from that, our two middle terms will be 2 times, right, what creates the middle term, 2 times x. So we use this to get our middle term, and then our first and last terms come from here. Our first term is our first term squared, and our last term is our last term in the binomial squared. So we'll try this with another example. Let's use now x plus y squared. We take our first term squared. Our middle term is always 2 times the two terms, x times y. And then our last term squared. We multiply this out and we get x squared plus 2xy plus y squared. And that is the product of that binomial squared. We can take a little more complicated example, this time 2x minus 5 squared. Then we take our first term squared, giving us 4x squared. Our middle term is 2 times each term here, and then our last term squared. Okay, I multiply this out. My first term, 4x squared, here 2 times 2x times negative 5 gives me a negative 20x plus 25. And that then is my final answer for this binomial squared. Next, we'll take a look at some power rules. Let's start with 2 squared. This gives us 4. 2 to the first is 2. 2 to the 0 power is 1. Again, following that pattern there. 2 to the negative first then is 1 over 2. Again, each time dividing by 2 to get our next term. So 2 to the negative second should be 1 over 4. Another way we can look at this is 1 over 2 squared, and this is 1 over 2 to the first. What we can then pull out of this is that anytime we have a negative exponent, we can rewrite it with a positive exponent by moving it to the denominator. So for example, x to the negative second is the same as 1 over x squared. Here again, just taking the reciprocal of this term and making my power now positive. This also works if I have, say, 1 over x to the negative third. I can rewrite this with a positive exponent by again taking the reciprocal, moving it from the denominator now to the numerator. My power again becomes positive. So negative exponents, we can make them positive by moving them either from the denominator up to the numerator or from the numerator down to the denominator. Some more power rules. If I have x squared times x cubed, this is the same as x times itself, being multiplied by x times itself 3 times. This gives us x to the fifth. What we see here is when we're multiplying things with the same base, we can add their powers to get our new power. So if we had x to the negative third times x squared, here we get x to the negative first, which is the same as 1 over x. And that then is my final answer. If I have something in parentheses, say x squared, and I raise that to the third power, this is saying x squared times itself 3 times. This then, adding my powers, gives me x to the sixth. So what I learned here is that if I have a power to a power, I can multiply them to get my new power. So for example, say I had 2x cubed to the negative second power. Everything inside here gets raised to that negative second power. So 2 to the negative second is 1 over 4. And x cubed to the negative second is x to the negative sixth, which is the same as x to the sixth in the denominator. So this then is my simplified answer using all positive exponents. If I am dividing, say x to the fifth over x squared, this is the same as x times itself 5 times, all over x times itself. Here my x's cancel out, and I'm left with 3 x's in the numerator, or x cubed. What we can derive from this is that we can find our new power by subtracting our powers. 5 minus 2 gives me my new power of 3. So for example, if I have x to the seventh over x to the second, 7 minus 2 gives me x to the fifth. Or if I had x cubed over x to the ninth, this gives me 3 minus 9, or x to the negative sixth, which is also 1 over x to the sixth. Another thing I can learn from this is my higher power minus my smaller power gives me my new power. 9 minus 3 gives me my new power of 6, and then that term stays where the larger power was originally. So if my larger power is in the denominator, my answer is in the denominator. So 9 minus 3, 6, stays in the denominator. Here we had 7 was my higher power. 7 minus 2 gives me 5. 7 was in the numerator, so my answer stays in the numerator with my new power of 5. What then if I have x over y squared raised to the third power? Again, everything in here gets raised to that power. So I have x cubed over y to the sixth, and that is my final answer. I can throw everything together now. Say I have x squared over x y cubed, and I raise that to the negative third power. This then is x to the negative sixth over x to the negative third, y to the negative ninth. And to simplify this further, my higher power here for the x's is negative 3. Negative 3 minus a negative 6 is a positive 3. So I have down in the denominator x to the positive third. And then y to the negative ninth, I want to make this positive, so I move it to the numerator, and I have y to the ninth. So this then is my final answer. We can use our power rules with scientific notation Scientific notation takes long numbers like 6,750,000 and rewrites them in a shorter form. To do this, I take my decimal and move it to just to the right of my first non-zero digit. So right here. When I go from left to right, 6 is the first number that is not 0, so I place the decimal after it. So now I have 6.75. I can drop the rest of the zeros, and I have this times 10 now to the 6th power. To the 6th power because I moved my decimal place 6 places to the left. 10 to the 6th is 1 million. And 1 million times 6.75 gives me back my 6,750,000. I can also do this with small numbers, say for example 0.000023. To rewrite this in scientific notation, again I take my decimal place just to the right of my first non-zero digit. So I have 2.3. Now I multiply this by 10. Now moving my decimal place in the opposite direction now, so I'm going to have negative 5th power. Again, I'm taking this really small number and writing it as a larger number times 10 to some power. So my power then is negative, since 10 to the negative 5th is 0.00001. Then multiplying this by that 2.3 gives me back my original number. So, taking a large number, I move my decimal place, and my power, right, is a positive number for the number of places I move my digit. Moving a small number, right, my decimal place becomes negative. Using this, let's take 2.38 times 10 to the 10th power all over 3.05 times 10 to the 8th power. To work this out, I take my numerator divided by my denominator. That is about 0.78, rounding that now, and 10 to the 10th over 10 to the 8th. Again, I have my power rules. 10 minus 8 gives me my new power of 2. This, however, is not in scientific notation. To fix that, I need to move the decimal place just to the right of my first non-zero digit. So I have 7.8. Again, here I'm making a smaller number larger, so I need to decrease my power here by 1 power of 10 down to 1. So I have 7.8 times 10 to the first. This then is now in scientific notation, or in standard notation I would have 7.8 times 10, 78. For multiplying scientific notation, we can take 6 times 10 to the 4th and 3 times 10 to the 3rd. Multiplying these together, I have 6 times 3, 18, and 10 to the 4th times 10 to the 3rd. Same base, we add powers, so we have 10 to the 7th. This again is not in scientific notation. I need my decimal just after my first non-zero digit, so I have 1.8 times 10. Now I took a larger number and made it smaller, so my power increases by 1 power of 10 to the 8th. So 1.8 times 10 to the 8th, and that is my final answer. Lastly, we're going to divide polynomials, but in order to do that, let's first take a look at fractions and see what happens with this. A over d plus b over d. When I add fractions, I add the numerators and keep the denominator the same. This gives me a plus b all over d. This will be important because we'll be taking polynomials divided by monomials, and it will be much easier to rewrite them as monomials over monomials. For example, if I take x to the 5th plus x cubed divided by x squared, I can rewrite this as x to the 5th over x squared plus x cubed over x squared. These are much easier to simplify, and I have x cubed, right, my 5 minus 2 to get my new power, and 3 minus 2, new power of 1, so just x. So this then is my final answer. What I can see from here though is that each term in my numerator is being divided by my denominator. So I do not have to rewrite this every single time. I can just remember to take that first term divided by the denominator, my second term divided by the denominator. So let's try this with another example. Let's say I have 20x to the fourth plus 10x, all divided by 10x. Here, I take my first term divided by 10x. 20 over 10 is 2. Next to the fourth over x, x cubed. Now my next term, 10x divided by 10x, is 1. Anything divided by itself is 1. So just have plus 1. Again, those two cancel out, leaving me with that factor of 1 that I have to bring down. So this then is my final answer. Let's do one last example. We have 3y squared plus 2y minus 12, all divided by 6y. Now I simplify here each term. So 3y squared over 6y, 3 over 6 reduces to 1 over 2, and y squared over y is y. Here 2y over 6y, 2 divided by 6 reduces to a 1/3. And y over y cancels out, just leaving a factor of 1 that I do not have to include here, since 1/3 times 1 is 1/3. And then negative 12 divided by 6y, negative 12 over 6 gives me a negative 2. Since there's no y here, I want to keep this y, I'll just keep it in the denominator. So my negative 2 over y. So this then is my final answer. This is the simplified form of this division problem. And that will do it for the last 3 sections of Chapter 5. Next week we will be taking a test over Chapter 4 and 5, so be sure to take notes on this and also complete the homework and quiz for this week over these sections. If you have any questions, feel free to email me or ask them in the discussion board, and I will see you next week for the test.